welcome to The Explainer. Today we're diving into a paradox that pretty much defines our digital lives, right? Think about it. Individual apps, websites, they fail all the time, and yet, somehow, the internet itself doesn't just collapse. So we're going to uncover the hidden architecture, the secret sauce of resilience that makes all of this possible. We'll go from some surprisingly radical ideas born in old-school phone networks all the way to the wild, decentralized world of blockchain. All right, let's jump in.
Okay, so let's just start with that big, central question. You've been there, we all have. Your favorite app freezes, a website just won't load. It's frustrating, but it's normal. But if every single piece of this massive digital puzzle can fail, why doesn't the entire system just fall apart? How is the internet still standing? What's holding it all together?
Well, to figure that out, we've actually got to take a step back in time, way back, to the original massive network, the telephone system. I mean, the demand for reliability there was, and still is, just off the charts. Joe Armstrong, who is one of the geniuses behind the programming language Erlang, he put it perfectly. He said, these systems are expected to operate forever. I mean, think about it. You can't just take the global phone network offline for a software update, right? It has to be built to just keep on running no matter what you throw at it.
And that right there, that gets to the absolute core challenge of any huge system. Failure isn't just a possibility, it's a statistical certainty. When you've got millions of lines of code, thousands of servers, guess what? Something is always breaking somewhere. So the real engineering puzzle isn't trying to prevent every single error, because that's impossible. It's about designing a system that can take a punch and just gracefully survive it. You know, decades ago, telecom engineers had to solve this exact problem. And they were working under some seriously extreme conditions. Just try to picture a telephone exchange. This thing has to juggle tens of thousands of calls all at once. It has to run nonstop for years without a reboot. And it needs to let engineers do software updates and even hardware repairs on the fly, all without dropping a single call. That's a huge ask.
So, faced with this monumental task, these engineers came up with something pretty radical. It was totally counterintuitive. Instead of trying to write perfect, bug-free code, which, again, at that scale is just a fantasy, they decided to do the opposite. They decided to embrace failure. Yeah, you heard that right. This was the core idea behind Erlang. What if? What if the safest thing a piece of your system can do when it hits a wall, when it sees an error it can't handle, is to just crash instantly? It sounds completely insane, I know, but it turns out it's the foundation of an unbelievably robust system. The whole philosophy, this let it crash idea, can basically be boiled down to three simple but super powerful rules. And trust me, these aren't just catchy slogans. They are the fundamental architectural laws that guide how you build the entire system.
Okay, rule number one, you build walls between everything, isolate it all. In Erlang, every little activity, like a single phone call, runs in its own tiny, lightweight thing called a process. Now, the key is, these processes are totally isolated from each other. They don't share memory, so if one of them crashes and burns, it can't take anyone else down with it. It's literally like having 1,000 workers on an assembly line, but each one is in their own separate, soundproof room. What happens in one room, stays in that room.
Next up, you create these things called supervisors. A supervisor is just another process, but it has one single, solitary job: to watch a group of those worker processes. Think of it like the manager on the factory floor. The manager doesn't actually build the cars, right? They just walk around, make sure all the workers are doing their jobs, and if one of them, falls over, the supervisor knows exactly what to do. So what this creates is this really simple, super predictable cycle of recovery. It goes like this. A worker process, maybe it's handling a call, hits a weird bug, and boom, it crashes. But because of that isolation, it crashes cleanly. The supervisor, who's been watching, sees it happen instantly. It logs the error and then just restarts that worker process from a known, clean, fresh state. It's ready for the next call. And the best part? The rest of the system, the other 999 workers, they never even noticed. It's business as usual.
Okay, so this whole model of managing thousands of these tiny, independent processes, it naturally leads to a bigger question. Who's in charge of making sure all these little tasks actually get a chance to run? You can't just have chaos. This problem, what we call concurrency, has led to two really different ways of thinking in modern software.
So you've got these two major philosophies. On one side, you have the Erlang way, which is what we call preemptive scheduling. Think of this like a really strict traffic cop at a busy intersection. The system itself, the virtual machine, is in charge. It decides when each task gets to run and for exactly how long.
It'll literally pause a long-running task to make sure nobody gets stuck in a traffic jam. Then, on the other side, you have the approach used in languages like Rust, which is called cooperative scheduling. This is more of an honest system. Each task runs until it politely raises its hand and says, "Okay, I'm at a good stopping point. Someone else can have a turn now." It's super efficient, but it completely relies on every single piece of code being a good citizen and not hogging all the time.
Now, this whole idea of isolating work, of having these tiny little units of failure, it's evolved way beyond just programming languages. We've taken that concept and basically scaled it up to a global level, to the very infrastructure we all build on today.
And that brings us to serverless architecture, sometimes called functions as a service. Now, the name is a little misleading, right? Of course, there are still servers somewhere. The point is, you, the developer, you don't have to think about them at all. You just write these small, focused functions, and the cloud provider like Amazon or Google spins them up in a temporary container whenever they're needed and then shuts them down. It's pretty much the ultimate abstraction of that original worker process idea we were just talking about.
But, like everything in engineering, this incredible abstraction comes with its own set of trade-offs you have to think about. For one, you get kind of locked into your cloud provider. Moving your code from, say, AWS to Google Cloud can be a real headache. Testing also gets way more complicated because now you're not just testing one big application, you're testing how dozens or even hundreds of tiny little functions talk to each other. And there's this one kind of scary gotcha that one of our sources pointed out. Some cloud providers have account-wide limits on how many functions can run at once. So you could be running a big load test on your staging environment and accidentally trigger a limit that shuts down your live production app. Ouch. So, what if even relying on a single cloud provider is too much of a central risk for you? What if you need the ultimate, absolute level of resilience? Well, some systems are now taking that let-it-crash philosophy to its logical extreme. They're getting rid of the central authority altogether, and this brings us to a world where, in a way, everyone is a supervisor.
And this is the whole idea behind using blockchain technology for things like the Internet of Things, or IoT. Think about it. Instead of your smart thermostat or your security camera trusting a single company's server, that trust is spread out across a whole network of participants. Everyone on the network holds a copy of a shared, unchangeable record of events, what's called an immutable ledger. This makes it incredibly difficult for any one person or any single point of failure to cheat the system.
This architecture here shows you exactly how that works. Down at the bottom, you've got all your IoT devices, your sensors, your cameras, whatever. Their data gets handled by this blockchain layer that acts like a decentralized gatekeeper. It uses things like smart contracts and that distributed ledger to verify who's who and manage access before any data gets passed up to the applications. So the key takeaway here is there is no single server to attack. There's no single point of failure that can bring the whole system down. So, as we've seen, from those Erlang processes designed way back in the 80s to today's serverless functions, all the way to blockchain nodes, we see this one theme over and over again. There is no perfect solution. There's no silver bullet. There are only trade-offs. Every single architectural choice is a balancing act. And you know, this whole dilemma is captured perfectly by something called the CAP theorem. Now, to get your head around it, just imagine two bank tellers, and suddenly their computer network goes down, so they can't talk to each other. A customer comes in and wants to withdraw money. Now, the tellers have a choice. They can choose consistency. That means they refuse the transaction until the network is back up and they can confirm the exact account balance together. They prioritize making sure the data is perfectly accurate. Or they can choose availability. That means they let the customer withdraw the money, even though they can't be sure about the balance. They prioritize being online and serving the customer, but they risk an overdraft if the other teller also allows a withdrawal. The CAP theorem basically says that when that network partition happens, when the tellers can't talk, you can be consistent or you can be available, but you absolutely cannot be both at the same time. And this forces every single architect to answer one fundamental question. If you're building a banking system, you're probably going to sacrifice availability for consistency, right? You need the numbers to be perfect. But if you're building, say, a social media feed, you'll probably sacrifice perfect up to the millisecond consistency for availability. It's better to see a slightly old post than nothing at all. And that choice, right there, between being correct and being online, that is the ultimate trade-off in the architecture of resilience. It's a question with no single right answer, and it's what makes building these massive, complex systems so endlessly fascinating.